We're now approaching the end of the semester, and this is the last class for which there's going to be formal presenters. The topics were going to be the progress made this semester and last semester of working groups 2 and 3, which are the SAMSI working groups devoted to time series analysis, and we're going to hear the postdocs who are leading or organizing those 2 groups, Hyungsuk and David Jones, give informal presentations of what those groups are doing. I would like to declare that next week is canceled. It says TBD, maybe we'll fill something up, but we're not going to. And then the last class, which is 2 Wednesdays from now, is when student presentations will occur. And I will contact the students by email next week to say, okay, next week, what's your title? Are you going to do it? How much time do you want? And I'll organize that by email. Okay? Okay, we'll start with tech.
Thank you very
working group
much.
number 2.
Well, I guess tech's part is going to be more. He's going to give a presentation of some work, and then we'll overview the.
Okay.
But this is related to working group 3. I guess.
Okay.
Oh, yeah.
So it doesn't really matter.
Yeah, I'm going to introduce a project from SAMSI ASTRO Working Group 3 about multivariate and irregular time series analysis. And today I'm going to talk about some statistical perspective of this project, which is about robust and accurate inference using some mixture of Gaussian and T errors. This is joint work with Justin Ellis. Justin Ellis is a postdoc at JPL, Caltech. And let me introduce what Pulsar timing data analysis is. I have a question to Ari. So
Yes.
Where does this Pulsar, the name Pulsar, come from?
1967. A grad student at University of Cambridge, Jocelyn Bell, was working over her Christmas vacation with charts, pen charts. There were no computers in 1967. From a radio telescope that didn't even have a dish. It was just wires put into the ground in Cambridge, Massachusetts. That's called the 3CR catalog. And she's looking at it, the radio sources go overhead. She's looking at it, and then she sees, she said, that's funny. I wonder what happened to the instrument. She's going through and going through. She saw it again. So she started analyzing it, analog, no computers, and she found about 30 times a second something went overhead that was going beep, 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 30 times a second. A pulsating radio source, Pulsar, pulsing radio. So then she went to her professor, and they consulted someone else. There was discussion of LGM, little green men. Okay, that was disposed of. They published it in Nature. 2 weeks later, Tommy Cornell, professor of physics at Cornell, said, oh, I predicted this, and he had, as a rotating neutron star, which had been predicted by a very famous person named J. Robert Oppenheimer, but never seen, predicted by quantum mechanics. So she essentially validated a new form of nature, of matter in nature. Okay. So then the Nobel Committee, some years later, gave the Nobel Prize to her professor, but not to her. And the Swedish Academy has never been forgiven for that, ever. So now they always make sure that the student, especially if it's a female student, gets credit along with the professor for these kinds of discoveries.
Okay, yeah. So Pulsar.
It's one of the most famous stories.
Yes, I very appreciate that story.
She's still alive, and she's still an astronomer, Jocelyn Bell.
Let's see.
I think she's Lady Jocelyn Bell. I think the Queen gave her something.
Wow. So Pulsar timing data analysis is related to modeling some gravitational waves. Have you ever heard gravitational waves? I think last year, astrophysicists detected gravitational wave for the first time. So let me show how this pulsar timing is related to gravitational waves. So here, two galaxies are merging. And inside these galaxies, there are two black holes interacting with each other. And this interaction of black hole generates some gravitational waves, which was displayed by a green coordinated surface. So there are gravitational wave coming. And this gravitational wave propagates toward our galaxy. It propagates to our galaxy. And within this galaxy, there is our Earth, and this is Pulsar. Pulsar is a lighthouse in the universe, and it sends pulses to the Earth in a very regular fashion. But because of the gravitational waves in the background, the arrival time of pulses deviates from the exact regularity. So astrophysicists use this deviation from regularity to model the gravitational wave, to detect gravitational waves. This is the data set from the realistic data set from Pulsar J1643. And when Justin Ellis approached me, he said, we have some problem of handling outliers, because usually Pulsar timing data have many outliers. So my question was, then how I can make his Gaussian error model robust? Because he already has some model based on Gaussian error, and he already has some sampler for this Bayesian model. So let me overview some errors. So Gaussian errors might be the most popular errors. Maybe you are using. Are you using some Gaussian error model? Yeah, because of its mathematical and computational simplicity. But Gaussian error makes some parameter estimation highly biased if there are some outliers. Student T error has the opposite pros and cons. It is very robust to outliers, but your parameter estimation can be less satisfactory because you're assuming unnecessarily heavy tail error assumptions on your most of Gaussian data. So my motivation was, then why not just mix these two to complement two errors? So I proposed the mixture error, that is Gaussian error with some probability, and T error with the other probability. So I propose this mixture error. This is the generalized p-dimensional mixture error with known variance components. I assume that we can accurately estimate these variance components, which is actually true in this field because astrophysicists believe that they know the measurement error variance. They calibrate it rigorously based on with their telescope. And here, ZJ indicates a latent outlier indicator. That is 1 if the model considers this datum as outlier. And ZJ is 0 in other case. And theta j is a probability of datum j being an outlier, because this probability determines the value of the latent outlier indicator. And alpha j is an auxiliary variable. I'm using this to express the T distribution as a scale mixture of Gaussian because it is simple to handle Gaussian distribution than handling T distribution. So I'm not sure whether you're familiar with this representation because here I'm using this representation. For example, random variable x follows some Gaussian distribution whose variance is alpha. And alpha also has some distribution, that is inverse gamma distribution. And the shape and scale parameters are the same as nu over 2. If we integrate out alpha, then marginally, this random variable x follows a t distribution with nu degrees of freedom. So this is well-known fact in statistics. I think he is a professor at Duke University. And actually, alpha doesn't necessarily have the inverse gamma distribution. It can be some exponential distribution so that the second mixture component becomes Laplace distribution marginally. So in that case, maybe used for model selection in high-dimensional cases, because Laplace distribution is the lasso in frequentist term. But for our purpose to model outliers, I'm just using inverse gamma distribution to make the t distribution. So this proposed mixture error marginally reduces to a Gaussian error if the outlier indicators are fixed as zeros. I mean, if zj is 0 for all j, then this is Gaussian error, marginally. And it reduces to a t error if the outlier indicators are fixed at 1. And it reduces to the target to the mixture of Gaussian and t error, and to a mixture of two Gaussians if the auxiliary variable is fixed at a constant, for example, maximum likelihood estimate. And this approach is used by statisticians and some astrophysicists recently. And actually, what I'm adding here is to make a bridge between t error and the mixture of two Gaussians. I'm treating this additional, the increment of the second variance component as random, using some prior distribution of inverse gamma. So this is the solution to his problem. I said he has some Gaussian error model, and he has also the corresponding sampler for his model. So converting his Gaussian error model into a mixture error model is actually simple. I multiply this magic term to the known variance component with their prior distributions. So I just simply multiply this term to the known variance component. And implementation of this mixture model is also simple because we can use his sampler. In his sampler, I replace his known variance component with the modified variance component. And then I sample some parameters from his sampler. And given these updated parameters, I updated some outlier-related parameters. And I repeat these two procedures to make a Gibbs chain. So here I prepare 3 examples, and the first one is the simplest one. Here I generate 20 realizations of a standard Gaussian distribution. And the second and third data sets are the same as the first one, except the last observation is incorrectly recorded as -10 or 10. And I assume that the mean of this generated Gaussian distribution, which is 0, is unknown, is the only unknown parameter of interest. And I set up 3 models. The first one is Gaussian error model, which is the same as a regression with an intercept term. And the second model uses t error, which is with 4 degrees of freedom, which is recommended in some famous book written by Andrew Gellman et al. And I derived the mixture error model by multiplying this magic term to the known variance component with their priors. So here is a sampling result. I display the marginal posterior density of mu based on 1 million posterior samples. So in the second panel shows the result without outlier. So without outlier, the Gaussian error model produces the posterior density that is highly concentrating on the generated true value. I mean, the Gaussian error model is denoted by dashed black curve, and that is concentrating the most near the generative value. This makes sense because we are assuming Gaussian error on Gaussian data. So this is correct answer. But as you can see, the solid red curve has the widest spread. Solid red curve represents the T-error model because we are assuming some unnecessarily heavy tail error assumption on the Gaussian data. So you are losing some estimation efficiency. The dotted blue curve represents the mixture error model. And this dotted blue curve actually passes in between these two curves, because mixture error is a weighted average of the other two errors. But in this case, the dotted blue curve is close to the dashed black curve because the data are Gaussian. But in the presence of outlier, the distribution from Gaussian error model deviates from the generative value because Gaussian error is sensitive to outlier. But the other error models are robust. I mean, they maintain their shape near the generated true value. So the mixture effect is maintained robustly. I mean, I didn't explain. The mixture effect is, in this case, without outlier, the dotted blue curve passes in between the other two curves. Because mixture error is maintained robustly, the mixture error has an advantage in terms of estimating the parameter. But there is no free lunch. Actually, the density curve of Gaussian error model can be drawn, less than a second. And T-error model uses 11 CPU time, 11 seconds, and the mixture error model uses more than double. So because you are updating more parameters at each iteration. Ask me any question if you have. The second example is about analyzing quasar light curve. Quasar is a very luminous object in the universe that has a black hole in the center that is actively accreting. So I analyzed one of the mature quasar light curves. Here I displayed the real data. And I actually simulated one because analyzing observed data doesn't tell me which one is correct. So I tried to mimic the observed data as much as possible, reproducing some outliers here. So this is a Gaussian error model based on the Ornstein-Uhlenbeck process. This is what I talked about last time and last semester. So the observed brightness follows some Gaussian distribution because I assume that the measurement error follows Gaussian distribution. And the latent true magnitude, the latent true brightness follows a multivariate Gaussian distribution. Actually, this is the solution of the stochastic differential equation of the Ornstein-Uhlenbeck process. And this Ornstein-Uhlenbeck process has three parameters, mu, sigma square, and tau. Mu is the overall mean of the process, and sigma is the short-term variability of the process, and tau is the time scale of the process. The full posterior density is the multiplication of all the density functions based on these distributions here. And we can use a Gibbs sampler to sample the full posterior. Actually, we don't need to understand whole model. My point is, I convert the Gaussian error model into a mixture error model by multiplying this magic term to the known variance component. And I define some prior distribution on the extra parameters outside of this Gaussian error model. So here is a sampling result, and the upper panel shows the sampling result of simulation study. Here, actually, Gaussian error model Gaussian error model produces the most accurate estimate on mu, but estimation of the other parameters has highly biased. But the other two error models, like T error model and mixture error model, produces the distributions centered around the generative true values. And actually, mixture error produces distribution closer to the generative value. Actually, this pattern appears in analyzing realistic data on the bottom panels. Yeah, although it's slight improvement, yes. So I also summarize some sampling results of a simulation study. Here, let's see mean square error ratio. This ratio means that mean square error of posterior mean of this estimate obtained by Gaussian error model over the same mean square error obtained by mixture error model. So if this mean square error ratio is less than 1, that means the mixture error model performed worse than the others. But the gain of the mean square error ratio for the other parameters is huge on log scale. So I think gain is much larger than loss in this mu estimation. Of course, it takes more CPU time. Running Gaussian error model takes 45 minutes, about 45 minutes, and running mixture error model takes 50 minutes, 5 minutes more. So let me come back to the Pulsar timing data analysis. I showed you the data here. I'm actually modeling this data now. So some astrophysicists model this time of arrival, the variation of time of arrival with some factors. So WM means white noise, measurement error component. And you know what I'm going to do here. I will multiply magic term into the variance component of white noise. And TM indicates the timing model. This is a deterministic physical model. And EC indicates the correlation on short time scale, on microseconds. And DM indicates dispersion measure variation. That is to account for the interstellar medium that the gravitational wave propagates through. And RN indicates red noise. That is to account for low frequency autoregressive noise. And actually, when we analyze a single pulsar data, this red noise term and gravitational wave term is not distinguishable. Okay. Here, this is the actual data we are analyzing. That is the observed time of arrival minus the deterministic prediction of timing, arrival time. Because this physical model is not complete, it actually has some residual on this timing model. And I'm accounting for white noise, the timing error model, and short-term correlation, dispersion measure, and timing red noise, and gravitational waves. And actually, my collaborator is using, astrophysicists in the field use Gaussian process to account for this autoregressive noise. So in a simplest setting, we can say their model is like this. So for the white noise, they assume a Gaussian error with known variance components. V is diagonal matrix whose elements are the measurement error variance. And for all these terms, for all these factors, we can assume this is a multivariate Gaussian distribution. And the first three factors are modeled by this T matrix. This is a deterministic, completely known design matrix. And the red noise and Gaussian wave, gravitational wave part is modeled by this B matrix. And this B matrix is completely determined by two parameters. And actually, this B matrix, the whole term is the spectral approximation to the Gaussian error covariance matrix. I think this is very complicated part in the paper, so I just simplified this because it catches all the core of the model. So the observed residual follow a Gaussian distribution with a convolution of covariates because I assume that each factor is independent. And the likely function is simply the Gaussian density with as a function of parameters. And I set up some proper prior distributions. And Pulsar is just multiplication of likelihood and prior. But my collaborator doesn't use this model, and he uses a hierarchical model because he says this small b vector has also some physical meaning. So this is actually the model he's using, and I multiply this magic term to the known variance component, setting some prior distributions. And then I run. So this is another simulation study before I analyze the real data. So these are, the blue dots are simulated data points. And the yellow and orange crosses are the synthetic outliers he entered. And the red dot means that our model considers these four outliers as outliers. These four synthetic outliers as real outliers. Our model doesn't consider this synthetic outlier as outlier. And here I display the fitted values, the trend. The yellow curves indicate the fitted curve based on Gaussian error model. And the green curve indicates the fitted curve based on mixture error model. So as you can see, this yellow curve is trying to describe all the up and down patterns of the data, trying to account for that outliers too. But the mixture error model tries to catch the overall pattern, not swayed by the up and down of fluctuations of the data points. So actually this makes a big difference. So here I display the posterior distributions of two parameters. So these three panels show the results from Gaussian error model. The blue one is from is the original model, and the orange one indicates his hierarchical model. And I added the magic term, and I reproduce the distribution from robust errors. So actually, the robust error model catches the true values of two parameters, but Gaussian error model doesn't catch the true value. Actually, this contour is located at around here. So this is the simulation result. And let me go back to the real data analysis. Here I displayed the posterior distributions of two parameters. The first row indicates the posterior distribution of log 10 of A, and the second one indicates posterior of gamma. Actually, the inference result on log 10 of A is similar, although the mixture error has higher peak. But the inference on gamma can be different for each parameter. Like if you use Gaussian error, then gamma estimate would be near 0. And if you use T error, then your estimation would be near 2.5 with higher standard error. And if you use mixture error, then actually it has a little peak near 1.2 or 3. Of course, it takes more time. I mean, that's the disadvantage. So here is a conclusion. I think mixture error model can be a more efficient choice and more robust choice compared to the other single errors. And it is simple and always possible to convert any Gaussian error model into mixture error model. And the implementation is not that difficult as long as you have your own sampler based on Gaussian error model. So I feel that it takes more CPU time, but I personally think that's not that expensive for accounting for outliers. And actually, this is the end of my talk. And do you have any questions?
So what if you, could you do something in like the multivariate, like variance component case? Because here you just multiply it by like a scale, they also do the scale.
Yeah.
So you could do maybe the same thing with like inverse Wishart distribution or something?
We can do that, but in for example, suppose each observation is multivariate, like p-dimensional. So in that case, each...
Well, maybe not even the multivariate, sorry. I just mean like if you take the error variance, the VJ matrix, and the off-diagonal components are possibly...
that is for a scalar case.
Yeah.
I mean, when each observation has some scalar value.
Right.
So your question is about when it has some factorized observation,
Yeah,
each
like
observation.
doing the same thing for the whole matrix VJ.
Yeah, we can do that, but it doesn't necessarily Wishart, because when you multiply scalar alpha to the matrix, and if you integrate the scalar alpha, then it becomes, the multivariate Gaussian becomes multivariate.
Oh, right, and that might not be the case with the, do you know what it would be?
I think I know what you mean, inverse Wishart.
Do you integrate that? I don't know what it would be.
Yeah.
You're saying not multivariate, though.
Yeah, it's not. I'm not sure whether it is multivariate T or not. But at least as long as we are integrating a constant, scalar constant of alpha to either scalar variance component or matrix variance component, I think it's multivariate T in any case. Oh, yeah.
So what is gravitational wave? Is it kind of a wave in space-time or something like that? I don't know.
Eric, could you explain what?
Sorry, do you explain what?
Gravitational waves.
Every time you move any mass moves in the universe, waves go out at the speed of light in space-time. But it's so minute that it's absolutely undetectable, except for the most extraordinarily strong gravitational fields, like two colliding black holes. That's what was discovered in 2015.
So they detected gravitational waves when these two black holes are colliding.
So it is kind of a wave in space-time.
Yes.
Thanks. So if you don't have any questions, then I will turn to Dave.
Okay, so this is, let me just plug my laptop in.
So this is not really going to be like a formal presentation, but the idea is to talk about what other working groups is SAMSI doing other than, say, like in this room, in this class. So I've just kind of, there's two working groups that are sort of looking at time series particular. Working group 2, which is called time series and synoptic surveys, and then working group 3, which is kind of multivariate time series and is related a lot to LIGO data, which is gravitational waves. So a lot of the people involved in working group 3 are looking at gravitational waves, whereas in working group 2 is more like people are interested in classifying light curves. So different types of star, you observe the variation over time. What type of star is it? So that's what they're. So I'm just going to show various documents that people have put together, but first, oh, this is not the one I wanted to show first. Okay, so this one, so Ashish at Caltech, I think he presented here, right? So this is some slides that he had to just give an overview of what working group 2 is doing. So I guess this bottom bit is just showing, you know, that's the other thing I opened. It's just showing some variable source, right? And so that's what they're mainly interested in. They're mainly interested in classifying variable stars, okay? So anything you're interested in, just say, because I don't know everything that's going on in working group 2, I just have like the general picture. So there's here's different working groups, different things they're looking at. So the working group 2 is divided into subgroups because it's kind of ended up as a lot of people, so they divide it into different subgroups. So one thing they're doing is a data challenge. So LSST, the telescope being built, is going to have going to detect many sources every night, and then they need to have some process for how are they going to classify those different sources. So they're interested in, people are interested in having a data challenge to get some good classification algorithms. And they're going to try to make it accessible to both astronomers and statisticians, because they might get some good methods from statisticians, but they need to make it sufficiently accessible, not depend on too much astronomy background. So these are the kind of issues that they're thinking about, and I'll mention a bit more of that in a moment. And then the second thing are these designer features. So to classify, if you're doing random forest or something, people collect a bunch of features and then run the algorithm and see what classification comes out. But they don't necessarily think very hard about what the features are. So they just collect whatever's in their data set, right? But you could try to think like, what are some physically meaningful features? So Ashish has found that there's a lot of features that are not very satisfactory. Like they don't really seem to do anything, and so he would like there to be some more intelligent features. Maybe, and this would also save a lot of time on computation, right? If you just have, say, 3 features that were classifying everything, that would be great. And then the next thing, the scheduling observations. This is something I've been working on, which is if I want to classify a source, when should I observe it? At what time should? If I can observe, if I have telescope time for a particular time, and there's 20 sources, or many sources that I'm interested in, which one should I look at? Eric has mentioned a bit about interpolating light curves, so that's another direction. Also incorporating ancillary information. So I think there's a slide on that. I'm not quite sure what the details are. So outlier detection is kind of a big thing. So LSST is going to observe many sources. Many of them will be types that we're kind of familiar with, but some of them will be new things. So how do we detect those new things? So we want to classify, but we also want to have an other class. So something that we haven't seen before. So how do we detect that? Group 7 on domain adaptation hasn't necessarily been, it hasn't been clear what exactly problem it's going to be tackling, but multiple people have been using domain adaptation, so I don't know if you're familiar with that, but I'll try to say a few things in a few minutes. But the idea is basically if you train an algorithm on a training set, but then you have a new data set that isn't the same as your training set, how can you still use your classifier? How can you kind of bridge the gap? Then there's light curve decomposition as well. And all these groups are kind of connected, particularly on the theme of classification, right? So let's see what else has been put in this. So, okay, so first of all, he was just going to say a few things about the data challenge. So there have been some other data challenges. Sometimes people put things on Kaggle. TAC has done a data challenge on time delay estimation. Maybe, did you give that presentation then? Time delay? Yes. Yeah, okay, so there was a time delay presentation. So there are various data challenges, but here they're interested in classifying sources. But they're trying to learn from other people's.
So I have a question. So in our time delay challenge, the key thing was whether participants know the generating process.
Yes.
Is it hidden in this?
Do they know it? I'm asking, in your time delay, did the people know?
Actually, we had a hint at the time. Like,
Okay.
there is some examples of analyzing quasar light curve using this models.
Yeah. So in some way, designing a data challenge seems like very simple. You just get some data, give it to people, say analyze it, right? But actually, it's not. There are many questions like, what data is the data? Should you use real data? Should you simulate the data? If it's real data, it's going to be better, as in more realistic. But you don't know the answer. So how do you deal with that? And then and it won't have all the complications. So like, which complications are you interested in people being able to deal with? And which ones are just kind of additional annoying things that you don't really care about too much. If you use an astronomical data set with lots of a real one with lots of astronomy in it, then maybe statisticians can't analyze it. So, or not without an astronomer anyway. So, so maybe you don't want to do that. Also, if you use existing data set, then maybe people can figure out which data set it is, and then they can somehow look up some work. So all of these things have kind of been discussed in this working group, this subgroup of what data to use and how to judge whether people are doing well. Like, what do we care about? What are we trying to achieve? That's, yeah, there are many issues. So I don't know if I have an answer. So this is just a summary of LSST. So this is kind of small, but it's LSST, and there's some kind of processing of the various data that they get. And like following up various classes, majority will be well understood, and so I don't know what else to say. That's just some reason why they want to have a data challenge to do this. So these are some of the existing catalogs that they could potentially use. Or what they may do is they may do something like they fit the light curve, a real light curve, and then they simulate. So then it's not exactly the same. And you also know what the truth is because you simulated from the fitted value, right? And so that you can do a kind of a half thing as well. And I think this is just a discussion forum of people are interested in a data challenge. So there's various groups who may produce a data challenge at some point. So these are some of the people involved. So yeah, this is the Catalina real-time transient survey. That's one that Ashish is one of the leaders of. And then there's I don't know about all the different surveys, but there are different ones. And of course, there's other things to consider, like, as I was saying, like what problems are you interested in solving? So some of these telescopes observe in multiple bands. So you may want a multivariate time series. You may want to, can we deal with multivariate time series well in classification problems? So in that case, and then you'd have multivariate features. So you might have a period, hopefully the period is not different in the different wavelengths, but other things could be different in the different wavelengths, like the amplitude of the signal. So you'd have a different feature for every wavelength, or every recorded wavelength. So the telescopes have different kind of data. So that's, okay, as I mentioned, like designer features. So the kind of canonical example which they have is this supernova versus non-supernova. So the supernova massive explosion. And people study supernova. They're very important in astronomy. So they've had these kind of 3 features that they've found are very important. So they've been looking at just classifying based on those 3 features. But they're specific ones rather than just random ones they picked out of some arbitrary data set. So I think they're minimum, I don't know what any of them mean. Minimum, star distance, prior outburst, minimum galaxy distance. Yeah, so I don't know why they're important, but that's some background. So scheduling observations, as I was saying, like you have some current kind of probabilities for what your source could be, and ideally you'd want to choose some time so that you can, get it as peaked as possible. If these are the different probabilities for the different classes, ideally you just have a huge peak on one class, and all the others would be 0. So. Yeah, we've been kind of using some basis models, and Stan, I don't know if you're familiar with Stan, and to do some Bayesian work. Yeah. So the idea is just that you have under 2 different classes of 2 different types of source. You have a model, and they're the red line and the blue line, and then you say at what point should you observe it in order to best separate the two models. And this is some like measure of the amount of information you'd get at different points. This is a kind of earlier plot, but anyway. Imputing time series. So here's a time series with lots of data missing. How do you kind of fill it in? So many methods kind of use sort of complete time series. So if it's not complete, how do you complete it? So how do you impute the rest of the light curve? This is James Lang. I wonder if that's probably James Long, right? Did James present in this class?
No, he
No.
did last semester.
Okay. Yeah. Oh, yeah. I guess he hasn't been back. Okay. So I guess these are some ancillary information. They're not the light from the star itself, but there's some other things such as the galactic latitude, the nearest galaxy, nearest radio source. Yeah, so I don't know why they're important, but I guess they are. Some ancillary information. So outlier detection. So outliers can mean different things. So you saw outliers from TAC. So they're outliers in the light curve, or it could be an outlier light curve. So which light curves are different to other light curves. So maybe it has a huge peak or something where you don't expect it. So that means it's different to other light curves that you've seen. So there's different types. So I think in this case, they're looking at the whole light curve rather than the points of an individual light curve. But I think the groups have been interested in both issues. So of course, then you can do, this classification, and then something that you get some probability for when it's not in your class, or you can do some clustering type thing. but it's not labeled, without labeled data. And Raphael is doing something on that. So the guy running the data challenge is doing something where he is, what's he doing? He's running, yeah, he's doing he's combining some clustering algorithm and then random forest. Do you remember how that works, Tag? No. So he's trying to detect outliers, but without having like defined classes. So he's doing some clustering first. Yeah, I forget the details of that. So, okay.
Yes, it seems to me that multivariate outlier detection without any knowledge of what's going on is usually multi-stepped. First, you have to do some sort of clustering or classification, and then you have to make some distance measures.
Yeah.
If a simple thing like a KNN, just a distance all by itself doesn't address general problems because there could be too many situations. You don't know what criterion to use.
Yeah.
So it doesn't seem like there's any simple method that always works.
Yeah. Yeah.
So, you sort of agree with that?
Yeah. I mean, obviously, the more knowledge you have of what's really going on, the better, right? So I think you've reminded me of how that works. So they do some clustering to get the classes, and then you can use random forest to put things in classes, and then if some of
by clustering, you mean a dendrogram, like a hierarchical cluster?
Yeah. So like not with labels. Yeah.
Right. I think what they say is that one of the nice things about that, if you have an outlier, is that it lives very far down. The node distance is greater than, you can do KNN on the node distances or something like that.
Okay.
It tends to live far away from the others.
Yeah.
On a tree,
Yeah.
if it's an outlier.
Yeah. Oh, I see. Yeah, I see. So they're using some.
I don't know what they're doing, but all I want to say is a dendrogram, a tree is actually a way of organizing the data that can find outliers relatively non-parametrically.
Yeah. So there's some things they're trying to do, and there's a lot. This is also related to the domain adaptation, which I guess is the next thing. Yeah, which is that there's a lot of this. We have multiple surveys. Some of the things are classified, some of them are not. Some classifications are reliable, some are less so. And so how to combine all that information. Like maybe you're observing in one wavelength of light, like X-ray or something, but the source has been observed in some other wavelength. So how to find the source from the other catalog and get the class. Is that class reliable? When you kind of overturn the previous classification. So there's lots of things going on there. So this is about domain adaptation. I think there's some better slides on domain adaptation, so I'll come back to that. So light curve decomposition. So they're looking at karma models, so autoregressive models to model various time series data. And then there's some things that are kind of not exactly SAMSI, but also related. And these are very necessary because a lot of data is irregularly sampled. So I guess that's so as I mentioned at the beginning, there's these various subgroups, but they're all kind of related, and they're all trying to sort of do classification and various aspects of that issue. So that's an overview from Ashish. Now I'll just show you a few more details about each of well, not each of them, but a few select things. So I mentioned so people are working on various documents. So this is the data challenge one. I've deleted some of it because I'm not allowed to show necessarily what they're going to do in case you take part. But there's discussion of what are the scopes, what's the scope, what number of classes do we want, what's the number of features, if we give people 10,000 features, is that prohibitive? Are they not going to analyze anything? How much, if we give people too much data, then it's just going to be whoever has the most computational resources are going to be able to do the best. So but then if you give them too few, they may do something that's very unrealistic for a large survey. So there's many things to consider. Who do we want? Astronomers, statisticians, computer scientists, and then some particular challenges. And then again, more on what do we want the data set to be? So the size of the data set. Should it be multi-band or not? Number of classes, number of features, types of features. Do we want to encourage people to come up with their own features, or should we just give them features and they come up with a way to classify things? So again, and then this discussion of simulated versus non-simulated data. So one possible path would be to use simulated light curves, resampling from existing ones with the cadence that's correct, the spacing, the time. And then what type of?
So technically, it's real data with simulated cadences. Which is slightly different than simulated data with real cadences, and that's different than simulated data with simulated cadences.
Yes. Yeah.
The point being that when we observe it is itself a whole, it's a time series issues by itself.
Yeah. Yes. And there's very many discussions about what the things should be, right, in the cadences.
Yes, I've heard that LSST is now in what's are known as the cadence wars. Now, the telescope isn't even built yet, and they're fighting over whether it's going to be well adapted to supernova discovery or well adapted to quasar discovery or well adapted to RI Lyrae stars, and goes on. There's dozens of other issues, and
Was it all round player? I thought LSSD is panacea for all.
yes, it's the in principle.
But that makes more wars.
If you get the right cadence, it's the panacea for everyone. But you can't get the right cadence for all the problems. So therefore, there's a cadence war. Therefore, it will do a mediocre job for everybody. Everybody will be unhappy. It will cost $1 billion, and everyone will be unhappy.
So is the problem of choosing one?
It's going to combine many different it's going to compete. There's no way to satisfy 1,000 astronomers. So,
Yeah.
I don't know if they realized when they started it was going to be so difficult. But what I think is that they're just not, they don't pay attention to methodology, they're interested in science. So something is going sharp, changed one, and they need to be rapid, whatever. But methodologically, 99% of the methods want evenly spaced data. That's what most methods in time series textbooks are about. So apparently, no one agrees to that one. Therefore, we're stuck with to develop our own methods that are designed for irregular spacing. I mean, there's a couple around, like Lobes-Scargill periodogram and Stellingworth periodogram. It's not as though there's nothing, but there's not as much. For instance, just something as simple as the autocorrelation function is not obvious exactly how to define it for irregular spacing data.
Yeah.
So what do you think about, will it be possible by LSST to extend the visible universe, or because it's powerful, that's why?
Yeah, it will, it's more sensitive, it will have better data than ever obtained by humankind of this kind of survey data.
Okay.
It will be phenomenal. And it will make many discoveries. The typical thing will be, let's just say, there's about 1 million quasars known, most of them found by colors and variability, some combination, often both. And it's going to find 50 or 100 million with the same criteria. And it will. So it's not as though it's not capable telescope. It's just that the people who want to find quasars have a certain pattern that's somewhat different than the people who want to find supernovae. And it will do the same with supernovae. We will find, I don't know the number specifically, but order of magnitude more. So it will be great for everybody, but everyone will be unhappy about how to analyze their data. And this issue of what are the features that will go into what time series algorithms in order to classify a quasar from a supernova, from an RLRA variable. These are issues that belong here at SAMSI. And since those guys are not going to give us nice data, we have to have general algorithms that work. Or if they don't work, we need to know how they don't work.
Yeah, and so all these things are kind of being considered in the data challenge, like what are LSST going to give people, and that's going to kind of determine what do we want to put in the data challenge. Because it's no good someone coming up with a method and then LSST gives them something completely different. Yeah.
Could I comment on the data challenge just specifically? Yeah. A few percent, I don't know, 5 or 10% of LSST time is something called the deep drilling fields, where they're going to go more often, deeper in certain small areas.
So what's the
They're going to be
definition of
high
deeper?
galactic latitude and in the galactic plane as well.
Okay.
And those fields, I believe, have been chosen.
Okay.
They're not interesting to us statisticians, where in the sky these are. But what I don't know has been chosen is what is the cadence of these the much richer cadences. It's not 1,000 points scattered over 10 years in some weird way, which is most of the sky. It's simply much richer.
Okay.
But what exactly is the pattern? I hope it's evenly spaced. I hope they go boom, 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 round in a circle so it's evenly spaced everywhere. That'd be the best for us, is we can then do Fourier transforms or whatever it is we want to do. So I think somebody at SAMSI should talk to some of the LSST people about the deep drilling cadences to optimize those for methodology. Because once for instance, we might be able to do the classification and then figure out, define RLI as these 10 features are the best or something. It may not be obvious except for the deep drilling fields. You may get the best data ever obtained by humankind of this type. So it happens that the chair of the deep drilling science collaboration is a colleague of mine at my department, one floor away from me. So I don't speak to him very much, but that's one of his jobs.
Yeah.
He's brilliant. But if there is a well-organized, concerted statement that can be made, either by SAMSI or by the LSST Information and Statistical Sciences Collaboration, to his group, a document should be prepared and officially issued that might influence one aspect. I don't think we can influence the whole sky, but the deep drilling we might be able to influence.
So that's like a separate part of it?
Yeah, the word separate is not quite the word, but
Okay.
it is distinct.
Okay.
It is going to be 5 or 10% of the time will be
Okay, I
spent
see,
in
yeah.
deep drilling cadences. Other people are interested not in the cadences, but just the fact that it's going to be, let's say, 10 times more sensitive.
Yeah.
That's what they like about it.
Yeah.
But other people are going to like the fact that it has to be with richer cadences.
Yeah.
But they're going to be weird. They're going to be incredibly spaced. I mean, it depends. We can maybe ask, please give us nice cadences. For at least that 5% of the data. If anyone is interested, I don't quite know which subgroup this is. Okay. But if anyone's interested in this, I can liaise with the LSST ISSE. That's the collaboration that can. I don't think the ISSE is sort of prepared to prepare a document, but if SAMSI prepared a document, they can sign it.
I see. Yeah.
And they have some authority. And you have some authority. Most people don't know who you are, but SAMSI. So this is not, it's a political issue, but it's based on mathematics. Policy issue based on mathematics. No one's using mathematical thinking, to my knowledge. They're only thinking about stars and quasars and supernovae. They're thinking astronomically, not methodologically.
I think inviting LSST people is a good choice because in Strongest Time-Delay Challenge 2, we invite some LSS people this time. And they jointly generate data to use their knowledge in LSST.
I can give you one paper that did a simulation of one science problem for the deep drilling cadences, and I think they just guessed what cadences might be because I don't think there's a document that says that's decided.
Okay.
But nonetheless, this paper might be useful
Yeah.
if you're interested to see how somebody reasonably guessed.
Yeah. Yeah. Could be interesting. So for a particular problem.
Yes,
Yeah.
for exoplanet transit detection,
Oh, okay. Yeah.
which LSD is not otherwise designed for at all. But they said, by the way, you're going to come up with tens of thousands of exoplanets.
Okay. Yeah.
Just because it's such an incredible instrument. It's just going to wiggle its little finger and do some big new science without anyone realizing it in advance.
Yeah. Yeah. So this part of the working group has had lots of discussions like this of what we're looking for and what's to expect. So of course, if you have a data challenge, there's also the issue of do you want people to classify things? Do you want people to find new sources? Like, what do you care about most? So they have to have some kind of metrics for that. And yeah, so there's various things like that.
When do you think you implement this challenge?
I'm not sure, but I think that they want to put a data set together soon, and then I don't know how, like James Long particularly, I think, and Raphael are working on that. So
you already generated simulation.
yeah, I'm not exactly doing that, and I also don't want to say exactly what they're doing. But yeah, they were working on it. So they have done some things, yeah, and so they will probably. I think what they're thinking of doing is writing a paper of to introduce that data, and then they will have the data challenge. Because people may want to use the data for other purposes or other challenges. So how are we doing for time? Okay, yeah, I can just say a few more things about Working Group 2. So I mentioned one of the things I've been working on is like these templates for different sources. So this is an eclipsing binary. It has 2 dips, and this is an array Lyrae. The phase is plotted twice. It just has 1 dip, and the gray lines are kind of indicating variability across many sources. So how to construct such templates and what they're useful for. So I've been looking at kind of various basis methods, so like Fourier basis and B-splines. But you can also do things like functional data analysis. So you can basically get the covariance, you can get many light curves, and then you can get the covariance matrix for that, and you can do you can run PCA on that covariance matrix. And that gives you some eigenfunctions that can describe the light curves. So this is kind of related to the designer feature thing in the sense that it's better to have some basis that's specifically suited to your problem in some ways, rather than having generic basis, in the sense that you can have fewer basis functions and they'll be better suited to the things you're trying to model. If you just use a generic one, you may need many basis vectors in order to capture it. And so the computation is going to be longer, it's going to be more intensive, and that's going to be a problem if you're trying to run it on, say, 100 million stars. So that's one of the things. And then there are lots of things you can do. So once you have a template, it can be helpful for finding periods, because if you know what the shape should be for different classes, then you can both find the period and also try to classify. So so when you have a basis model, you represent each light curve as a sum of some coefficients times some functions, right? Like sine or cos functions. And by fitting to a training set, we can get a prior distribution for each coefficient. And then with a real light curve, you can kind of get a posterior fit for the different classes, and then you can do things like compute the posterior probability of each class, and that's what's shown on the bottom. Yeah. And then there's also this thing, and so that also leads into this scheduling thing. So when would you next schedule a point in order to get the highest probability for a single class, rather than it being spread across many classes? You don't want every class to be like 0.1 probability, right? You would rather one was 1 and everything else was 0. So if you know the shapes of the light curves, and you have some data, then you can choose when to observe it in order to and so it's kind of very obvious. You just choose in a kind of very simple setting. Not accounting for uncertainties, you just choose the point where the templates are most different, right? So that's the kind of intuitive thing. So that's some backgrounds on the kind of scheduling, and then I mentioned the domain adaptation, which is a big theme as well. So the data challenge, the scheduling, and domain adaptation are kind of the 3 biggest themes, I guess, in this working group. So how do we? How do you? So I'm not going to go through all of these. I just want to show a few brief things in case. Yeah. So you have one survey, one telescope, and you develop some classifier, random forest or something. Now you have another survey. Can you use the same classifier, or do you need something else? So that's the question that domain adaptation is trying to deal with. So this is the kind of classification. You can just draw some linear line. It's very easy in this case. But what if there's new data? Can you, from another source, can you also classify that data? So there's you can just base it kind of on which class it's near, and so that's the kind of simplest version. But what you can do is you can use your existing classifier to classify some of the data that you don't know the classes for. So these the training data for one survey and then the new data from a different survey, you can use your classifier to classify some of these points. And the ones you're kind of pretty sure about, you can now label them. And then you can kind of feed that into redoing a new classifier. So that's one of the kind of approaches in domain analysis.
Sound like just like online learning.
Yes, so they're very, they also call it adaptive learning.
Oh, so it's like the same basic premise.
Yeah, it's very related problems, yeah. So online learning could be, though, I guess, learning the thing initially. Whereas this is like you already have something, but it's just not for the right problem. Because you have a different telescope now, and you want to use your old method. So they're very related, but just slightly different, yeah. So there are different kind of, these are some different reasons why your distributions may be different. Like the underlying covariates may be different. In your training set, you may have a sample bias. Prior probability changes, I'm not quite sure why that would. I guess you could have different people. I'm not sure. And yeah, I guess you could oversample one case. I guess that's also some sources are much easier to observe than others. That's, I guess, somehow they're distinguishing that from sample bias. So because it's conditional probability. Okay, so yeah, this is trying to illustrate. So I guess this is the one I wanted to mention. So they're instant-based. So there are a number of ways of dealing with this, and one is to say, okay, so we have the labels for the colored data, but not for the other things. So one thing we could say is which of the colored things are close to the new data, and then just kind of, because since we have the labels on these, we can design a new classifier, but on the labeled data, and kind of hope that it works for the unlabeled data as well. And so that's the idea there. And then there's some kind of iterative approach. And then there's also a feature, so what if So you can try to get a common features, I think. Is that what that's saying? Yeah, so you can project onto a common space if they're just completely different. I'm not that familiar with that approach. And there's just some kind of limitations. Obviously, if you have your new data is just completely different to your existing data, there's no hope. Okay. So this is the active learning. So the active learning is you just have a bunch of points, and then you inspect some of them, and then you classify those ones. How many do you kind of need to go through in order to... not only how many do you need to go through, but which one should you choose in order to need as few as possible. So in this case, if you choose something near the line, it might help you more than if you choose something. So that's what they're trying to illustrate. So yeah, here you see they have both active learning and domain adaptation. Yeah, so I guess the active learning is which points would it be most helpful to learn, to be able to classify in the target sys, and then we can kind of feed that into how we're doing the domain adaptation. Yeah, so I don't know all the info for this. Okay, so that was that's the domain. So that's been a big. So in the data challenge, they have these different data sets, and people are interested in how you bring various information together. Okay, so now I guess. Tak, do you want to say a little about this image? So this is so we can move on to working groups.
People are focusing on gravitational waves. Seems weird. So this figure shows the same gravitational wave, but detectors can some detectors can catch some different frequency of gravitational waves. I think this is the LIGO, the gravitational wave detector in Washington and Louisiana.
So you know about LIGO? It has like huge lasers that go for how long, like kilometers or something?
It's 2 arms and
yeah, and so then by sending two lasers at kind of right angles to each other, they can see how long it takes them. When they come back, they can see if they're kind of out of phase. If they're out of phase, that means the space has kind of been warped. All right, so then they detect the gravitational waves.
so the LIGO detector is for high frequency gravitational waves, and the pulsar timing data analysis that I talked about an hour ago is about low frequency gravitational waves detection. And H, I asked my collaborator about H, and H means the change in the total distance, travel distance over the total distance. The distance change is caused by gravitational waves.
So what is this in meters?
I will ask that. Okay. So here, the pulsar timing data analysis is for, it's easier to detect gravitational waves because it changes the distance more than what LIGO can detect.
Yeah, so what LIGO is detecting is it's very, very difficult to detect. So the lasers are kilometers long, and if you like move next to it, your gravitational field will be detected. Okay. So it has to be extremely sensitive, and they have like one of the problems that they're discussing in working group 3 is they have many what they call auxiliary channels, which are things like the temperature of many places, the wind, many things.
So in this facility, there are many temperature, and they measure sounds or the.
So they need two, because if they get a detection, they want another validation one, and when they get a possible detection, then they not only check with the other detector, but they check all the auxiliary channels to see if the things coming in.
So this is the gravitational waves that this LIGO detector catching. One is in Washington and the other is in Louisiana.
So the left is.
So when two black holes are colliding, based on the description of array, it seems like. So, yeah, the same signal was catched in the other place, and so it was the first detection of gravitational waves. And actually, there, as Dave said, there are many other auxiliary measures like microphone, temperature, or whatever. And actually, we have those auxiliary time series data, and so this is one time series data, and there are about 300 other time series measured by the other auxiliary instruments. So our focus is among those 300 time series data, which one is correlated to this detection, this event. If we find those auxiliary time series data, then we can support the detection more clearly, like more strongly. So that's what we are doing right now. And actually, Working Group 3 has two subgroups. One is for this auxiliary time series data analysis, and the other is pulsar timing data analysis that I talked to you on our.
I thought you were going to say one's for the main channel and the other's for the.
Yeah, I mean, so this is what we are doing. So if you are interested, actually Somen is leading this group, so maybe you can be more exposed to this multivariate time series analysis. Okay.
Yeah, so I guess the only other thing I want to show, so maybe you can do this. I wanted to show them just the ASTRO workshops. I don't know if you've seen. Can you just go to the SAMSI website? Because there are many, like, if you want to find out about any more of these things, then there are many like videos and slides that people have put online. And astronomers have a lot of nice pictures. So if you're like want to do a talk, then often like it's good to get an idea of like what's so you can often get good motivation.
Where should I go to?
So go to like the ASTRO program. And so we had various workshops throughout the year. And
So one is in India.
Yeah.
In India, there was a workshop about time series analysis and gravitational waves, especially for light or leg data.
So you can click on it, yeah. And if you go down, then you see all the slides and videos from there. Yeah. So there's various things on domain adaptation here and gravitational waves.
I think the first part was about the time domain analysis.
Yes. So I think Matthew Graham's talk was very helpful. But yeah, there's just
At least.
yeah, I don't think we should write some videos. But yeah. So that's one workshop. So that, there are many things to see if you want more information. And if you go back, then there was one in October on exoplanets. I don't think there's any slides, but there's some information. Nobody has slides.
Show me yours. And there would be a transition workshop. I think this is not for this class.
Okay. So there are just more things you can find out about. So I guess that's. Did you have anything else? So I guess that's all prepared.
Okay, well, thank you very much, gentlemen. We ended a little early, but I think that's okay. Are there any comments? I think when we heard the various other researchers, let's say Becky Dawson or Ashish Mahabal or even myself, you heard a single scientist saying, this is what I and my colleagues have been doing for a few years on a single problem, and you got a more coherent presentation. SAMSI working groups are not like that. They're designed to be unanswered. In fact, even the questions are ill-defined when they start. And they develop questions, and they explore possibilities, and they have dead ends, and they have new opportunities emerge. And the net result is that even after considerable effort, we have what might be called sort of an adventuresome exploration of methodology for a given field. But it doesn't it's not ready to write papers usually. It's usually in some intermediate stage. So that's why I left this presentation to the very end of the course, so that you didn't get the feeling that everything is always disorganized, but that you got the feeling that it is disorganized at the edge. And that's what SAMSI is about.
Yeah, so I think as over the years, so yeah, I haven't. I started with some specific problems that I was already thinking about, and then I got enrolled in the working groups, and then I realized they were connected to other problems. So then I started doing like multiple different things and learned about. So in my case, I was doing the scheduling. I learned I should do maybe make some templates, and then I realized there are many ways of making templates, and various people have different suggestions, and that they want to use it for period finding or for classification. So there were many. So it just kind of evolved into many things. So I haven't. So now the kind of product of that for me is that I now have kind of 10 directions I can look at rather than one. So that's kind of, but I haven't necessarily answered any individual question completely.
I mean, sooner or later, some people will focus on some things and write a good paper and come up with a study. But while we're working as these groups, it's more open-ended.
And for a statistician, it's useful in that I've learned a lot of astronomy context, which I didn't appreciate before. So I had collaborated with astronomers before, but at SAMSI it's more like almost every day. Like I will talk to at least one astronomer, so I will gradually like build up a bit. So I think that's kind of helpful exposure.
Right. Improves cross-disciplinarity enormously. Okay, thank you very much, sir. We'll sign off.